In this video, we're continuing to look at trigonometric equations. However, instead of looking at ones where there's domain restrictions, now we're going to look at ones where there's going to be general solutions. So this is when x can be any real value, when x is a term that's such as sine x is equal to something tan x or cos x. So we'll look beginning at an example. So sine x is equal to a half. So sine x is equal to a half, then we know that when it's positive, so it has to be in the first and the second quadrants. So first and second quadrants. And then the general theta value, so that's like the base of the one you can think about, is pi on 6. Now that we know that, it's pi on 6, and then for the second quadrant it's going to be pi minus pi on 6, as that's that we have to get that value there to equal theta. So to get this value here, it's going to be pi minus pi on 6, and this will give us 5 pi on 6. So we know that for the first two pi's, so for the first circle, we have pi is equal to pi on 6, and theta x is equal to pi on 6, and then x is equal to 5 pi on 6. However, x is equal to pi on 6 plus 2 pi also satisfies this equation. So sine 13 pi on 6 also equals a half. And that's because what you're doing here is you're going around the circle once, like 2 pi, and then you're going pi on 6 again, so you get this exact same value. Then we could also go around the circle once, and then twice, plus pi on 6, and we can get the same value. So we can go x is equal to pi on 6 plus 4 pi this time, and it would still satisfy the equation. You could also do this for 5 pi on 6, so you'd have x is equal to 5 pi on 6 plus 2 pi, and then 5 pi on 6 plus 4 pi. This can also go in the negatives as well. So we could have x is equal to pi on 6 minus 2 pi. Because what you're doing there is you're going from the negative, you're nearly going all the way, but you're stopping just before you reach pi on 6. And you could also have pi on 6 minus 4 pi, because you're going all the way around once, and then nearly going all around the way twice, but you're stopping just before. And once again, you can do this for 5 pi on 6. So there's going to be a lot of solutions. So what we do is we do a general solution, which is we write it down, the solution, with regards to another variable. So there are two we have to write for sine. Firstly, we have when x is equal to pi on 6, and then you can add 2 pi, 4 pi, 6 pi, etc. So what we can do then is we can go plus 2 pi k. Then we write k has to be an integer. So what this means is that has to be an integer, an exact value. So 0, 1, 2, 3, negative 1, negative 2, negative 3. So note it can still be negative. However, this shows us all the solutions for pi on 6. And then for 5 pi on 6, we write another one. So x is equal to 5 pi on 6 plus 2 pi k. And then that will do the same thing as pi on 6 and will show all the different solutions. So therefore, the solution to sine x is equal to a half is that x is equal to pi on 6 plus 2 pi k, and also x is equal to 5 pi on 6 plus 2 pi k, where k is an integer. And when k equals 0, that's the solutions between 0 to 2 pi in this case. Or more generally, negative pi to pi. Now these two numbers here could be any number where you have pi on 6 plus 2 pi k, or it could be a larger number. So what I mean by this is that we could have here x is equal to 13 pi on 6 plus 2 pi k. And this will give us all the same solutions as this one here. However, when k is equal to 0, obviously these two x's are different. But there will be a k here that relates to a k here. So both these x's give the same solution. So here you have 2 pi k, 13 pi on 6. And that's because 13 pi on 6 is equal to pi on 6 plus 2 pi, which you could get from here. But rather than writing that, when you're writing these numbers here, you want to get the magnitude to be the smallest possible. So then you want these numbers to be between negative pi to pi, so pi inclusive. So that means when you're thinking what type of angles they can be, so if they're, let's say, here, then you look for this angle and the smallest value, don't look for a multiple. And when they're negative, so down here, then you look for this value here. So example, if we wanted pi on 6, so with pi on 6 we wanted the first and second quadrant, but if we wanted the third quadrant, then we could write negative 5 pi on 6, and that would give us the theta here of pi on 6. So that confuses you, don't worry too much about it. However, understand the first bit, understand how it's plus 2 pi k, and just remember here, you put try and put the smallest magnitude number you can. And if you're looking in the third quadrant, rather than going from the positive all the way around to the third quadrant, go from the negative. So you want these two numbers here to be between negative pi to pi. So that was sine. So what about cos? Well, cos x is equal to root 2 on 2. Now this is slightly different because in the unit circle with cos, we have the first quadrant's positive, the fourth quadrant's positive, and then negative, negative. So the positive and negatives are close to each other along this x-axis. So we have theta here, and then theta here, theta here, and then theta here. And because they're at a point, and then plus or minus that point, instead of writing two equations, we can write one. So we'll begin by thinking, well, what's the standard theta for root 2 on 2? That is pi on 4. So that's the standard one, and we want the first quadrant because it's positive, and also the fourth quadrant. So that means we want pi on 4 and negative pi on 4. So that means we can write that as pi on 4 plus 2k pi, and x is equal to negative pi on 4 plus 2k pi. And talking about what I was just mentioning, these two numbers are between negative pi and pi. So we have this 2 plus 2k pi, and you should understand how the plus 2k pi from the sine, it's the same thing with cos. We go around all the way once, and then we go a bit more and we reach this pi here. Or with a negative, you can plus 2 pi k, plus 2 pi, but just stop short, and you get this negative pi on 4. But also note that x can be a negative value. However, remember that you have to write k is an integer. But instead of having two equations, we can simplify this into one. So we can actually write that x is equal to 2k pi plus or minus pi on 4 when k is an integer. And that's for if cos is positive or negative. So this can be a general solution for cos. So obviously the pi on 4 will change. So this number here will change, but we'll always have 2k pi, and then plus or minus a certain number depending on what the original equation is. So finally, looking at tan. If tan x is equal to 1, then what's the general solution? Well, when tan is equal to 1, sine theta and cos theta must be equal, so therefore theta is equal to pi on 4. Now, which quadrant are we looking at? Well, it's positive, so we're looking at the first one, and we're looking at the third one. Now, there's something unique about the tan, and that's because when we have a solution, let's say pi on 4, then it's two quadrants over the one we want to look for. If it's negative, then it's a value here. Then it's two quadrants over the other one we want to look for. Now, if we want the two solutions, so x is equal to pi on 4 plus 2 pi k. So that's the first one plus 2 pi k. Then we can also have the second one, which is going to be negative 3 pi on 4 plus 2k pi. So how I got negative 3 pi on 4 was this value here has to be pi on 4. So to reach that from the negative, I went negative 3 pi on 4. So I got these two solutions, but I can actually simplify this into one. That is, I can write x is equal to pi on 4 plus pi k, where k is an integer. So instead of writing 2, I can write 1, but the big difference here is instead of plus 2 pi k, it's just pi k. And that's because if you've seen the diagram above, if you have one solution, you can get to the next solution by just adding pi. Then you can get to the next one after that by just adding pi as well. So instead of having two values that are in quadrants and are opposite, with tan, they are opposite. So because they're opposite, they're always going to have a difference of pi. And due to that, we can go from here, plus pi, to there, and then to there, and then across. So all these x values are exactly the same. So this and this, if you combine all these x values, you'll get the exact same here. And this is a general form for tan, if it's positive or negative, where you have x is whatever the number is here. So for the general, sort of whatever theta is, then plus pi k. So whatever the number is, plus pi k. But once again, remember that k can be a negative number, but that's okay because if you have this number here, instead of going positive, you can just go across here and you can take away pi. What about if the equation is slightly more complicated and it looks something like 2 sine 2x is equal to root 3. Then once again, we rearrange to get sine 2x is equal to root 3 on 2. And just like when we were looking at the previous video when we had a restricting domain, we let a is equal to 2x. We get a, for this sign, well, a will equal something plus 2k pi. And then a is equal to something plus 2k pi. So in this case, it's root 3 on 2. So for that, for pi, that's pi on 3. And because it's positive, it's going to give us pi on 3 and 2 pi on 3. Now we know that a is equal to 2x. So we sub a is equal to 2x. We can get the solutions for x, which is going to be pi on 6. So we've divided both sides by 2, plus k pi. And x is equal to 2 pi on 6, which can be simplified to pi on 3, plus k pi. Once again, writing that k is a integer. But if you have these sort of terms in the middle, even if you had, let's say, 2x plus 1, you let a equal 2x plus 1, then you solve for a, then you rearrange to get x as its individual term. But you do still have these k, which will give you general solutions. So in summary, we have these three general terms. We have x is equal to that, cos x is equal to that, tan x is equal to that. And this is when you have tan x, cos x, and then sine x. However, if you have some other terms in there, you'll let a equal that. Then a will look like this. Then you can rearrange to get in terms of x.